Lecture is entitled The Physical Principles of Gas Exchange. We're going to be covering various factors that influence the diffusion of gases, oxygen and carbon dioxide, through the respiratory membrane. So remember, when we talk about the respiratory system, there's a number of things that are involved. You first have to have the physical act of getting air into and out of your lungs, and that was pulmonary ventilation. The next aspect is the exchange of gases at the respiratory membrane, which is what we're going to be covering today. And then the next lecture is going to cover how we transport these gases throughout our bloodstream. So if we're picking up oxygen up in the lungs, we need to carry it to the tissues. And at the tissues, we need to pick up carbon dioxide and transport it back to the lungs. So that's what we're going to be doing next time. So let's cover some topics that you need to be aware of when we talk about the principles of gas exchange. So in the level of the lungs, you'll notice that you've got blood that's carrying carbon dioxide. It still has oxygen, but we need to pick up some more oxygen. In the alveolar space, we need to have oxygen diffuse across the respiratory membrane and then eventually into the blood. Some of it will be dissolved in plasma, some will be bound to the red blood cell. At the same time, carbon dioxide needs to go from the blood into the alveolar space and eventually we'll exhale it. So the first thing I want to talk about is something called Dalton's Law. The air that you breathe is a mixture of gases. Remember, there's a difference between a mixture and a compound. There's basic chemistry. So a mixture is composed up of more than one item, and there's no interaction between them. So if I have, say for example, 3 or 4 different color marbles, and I throw them in a pot, that's a mixture of marbles, and the marbles are not interacting with each other. So the air that we have is a mixture of a number of different gases, and each of those gases exerts what we call a partial pressure. So the total mixture of the gas is a certain pressure, and the atmospheric air at sea level is 760 millimeters of mercury. Well, that air is mixed up of nitrogen, oxygen, carbon dioxide, some water vapor, and some very minor gases, and each one of them exerts a partial pressure. And if you add up each individual partial pressure for the gases, you'll get this total pressure of the gas. So you can determine the partial pressure of a gas if you know the relative percent of that gas in that mixture of air. Well, it so happens that the majority of the air that you breathe is nitrogen. Nearly 79% of the air that you breathe is composed of nitrogen. Nearly 21% of the air that you breathe is oxygen. So let's try a math question. So if I have, I'm up a mountain, the partial pressure of the air that we breathe is going to be way less than what we have at sea level. At sea level, it's 760 millimeters of mercury. Well, at 10,000 feet above sea level, the barometric pressure, which is also your atmospheric pressure, is only 523 millimeters of mercury. So what would be the partial pressure of oxygen? So if you remember that about 21% of the air that you breathe is oxygen, and it doesn't matter if you're at sea level or up at the top of Mount Everest, it's still going to be nearly 21% of the air that you breathe will be oxygen. So if you take 0.21 times the total pressure for the barometric pressure, you'll get 110 millimeters of mercury. That would be the partial pressure of oxygen in atmospheric air. Well, it so happens at sea level, it's much higher than this. So if you'll notice that oxygen, again, nearly 21%. If you do the math, if barometric pressure is 760 millimeters of mercury at sea level, you get oxygen to be about 159 or 160 millimeters of mercury. You'll notice I've given you 2 numbers. The reason why I've given you 2 numbers is it determines whether or not you decide to round or not. So it's either 159 or 160 millimeters of mercury. So you'll notice when I'm at 10,000 feet above sea level, the levels of oxygen in the air, the partial pressure of the oxygen in the air is much less, which may become important when we talk about gas exchange at the level of respiratory membrane. You'll notice that carbon dioxide is a very small percent of the air that you breathe, only 0.04%, so its partial pressure is only about 0.3 millimeters of mercury. So I'm starting to show you a whole bunch of numbers, and yes, you do have to remember some numbers. So I will circle any numbers or values that you need to remember. So if you notice on the right, you do need to know the relative percent of nitrogen, oxygen, CO2 in the air that you breathe. And you can round it up. If you remember, nitrogen is about 79%, oxygen is about 21%, and carbon dioxide is less than 0.1%. It's 0.04% of the air that you breathe. I do want you to remember those numbers. You do also need to know the partial pressures of oxygen and CO2 no matter where I am. So you're going to notice as we go through the lecture, anytime we go look at atmospheric air, then look at alveolar air or humidified air, you always need to know the partial pressure of oxygen and CO2. So you need to know these two values here. So you breathe the air. The air is going to be moved down through the tracheobronchial tree, and the partial pressures of these gases are going to start to change. And by the time it gets to the alveoli, it will change again. So I want to review just very quickly right now that the composition of the alveolar air, which is right there where gas exchange is going to take place, is determined by a number of different factors. Obviously, atmospheric air. I've already told you that if you go to higher altitudes, you're already going to start off with a lot less oxygen to begin with. The other thing that I want to talk about right now is the actual humidification of air, because as air moves through the tracheobronchial tree, it will become humidified, which will alter the partial pressure of the gases. And then we're going to be looking at these three things, but I want to look at the humidification of atmospheric air. So what you'll notice is I have the chart with the partial pressures of the gases in atmospheric air, and next to it I have the partial pressure of the gases in humidified air. The water vapor, or I should say water vapor pressure, is determined by your body temperature, and we consider body temperature to be a constant. Fully humidified air, the water vapor pressure is going to be 47 millimeters of mercury. So this is assuming we're at 37 degrees Celsius. So in humidified air, and it will be fully humidified by the time it makes its way to the alveoli, the water vapor pressure is going to go from 3.7 to 47 millimeters of mercury. So what's so significant about that? Well, you'll notice is, especially if you look at nitrogen and oxygen, it has started to dilute out the other gases. So oxygen has now dropped to 149 or 150 millimeters of mercury. You'll notice I have the same value for CO2, but if I had taken this out to a number of different decimal places, you will see that it would have dropped, but you'll notice CO2 is so little to begin with, we pretty much are going to be 0.3 millimeters of mercury still in humidified air, but it has actually dropped though, because water vapor will dilute out the CO2 also. So what values do you need to remember again? Well, again, I've had them circled. So these are the ones, the previous ones you already told you to remember. You do need to know these values. So in humidified air, you'll notice as water vapor is being added to the air, the partial pressure of oxygen and CO2 will drop. The most significant one to be aware of is the partial pressure of oxygen has dropped. So first thing we look at when you finally get down to the alveoli, we started off at 159 or 160 millimeters of mercury of oxygen. It's dropping to 149, 150 before you hit the alveoli, and what you're going to notice is it's going to change again. Also, the partial pressure of CO2 is going to change again because of what's going on in the alveoli. So let's go back to this slide here again. These are the two things that first influence the composition of alveolar air. Next one, I want to look at this thing called partial replacement of each breath. So you'll notice this is just a little diagram of pretending these are the lungs. At the end of a normal exhalation, you have a certain volume of air in your lungs called your functional residual capacity, which averages about 2.3 liters or 2,300 mils. So when you take another breath in, you don't inhale 2,300 mils of air. That doesn't happen. You actually take in only maybe about 500 mils of air, and only less than that actually gets down to the alveoli. So if I asked you about how many breaths would it take to completely recycle the air that you have here already in your lungs, it's going to take more than one breath. It's going to be maybe about 7, maybe 8 breaths before you completely turn over the air in your lungs. That's referred to as partial replacement. So what is the significance of partial replacement? Is the values that I give you for alveolar air, for the partial pressures of oxygen and CO2, they will be fairly constant no matter what I do, and I'm even including exercise. Those values will be pretty much what I tell you, because the partial replacement, the gases aren't completely turned over in one breath, which is kind of important, and so we don't have sudden changes in the concentrations of the gases in your blood, and it actually makes the control mechanisms involved in respiration much more stable. So it prevents either excessive increases or decreases in oxygen or CO2 if respiration is disrupted maybe periodically. So I ask you to hold your breath or increase your breathing a little bit, the levels of those gases in the alveoli won't change too much. Now other things that will influence the partial pressures of the gases in the alveoli is going to be how quick the gases are exchanged, or also the rate in which, and I'm talking about, or I should say, the gas exchange at the respiratory membrane, and also the rate in which we bring in new air into the lungs or get air out of the lungs. So changes in ventilation may affect the partial pressures of the gases. And in the case of oxygen, the rate in which it's absorbed. So oxygen will go from the alveoli into the blood, across the respiratory membrane, so it will be absorbed. So I want to look at these graphs and show you a relationship between changes in ventilation or changes in the rate of absorption of that particular gas, in this case obviously oxygen. So I want you to look at the red line, the red graph. So we have a dot right here. This represents the normal absorption of oxygen, which is about 250 mils of oxygen move across the respiratory membrane per minute. And that's a number to kind of put in the back of your head, because I'm going to be mentioning that later. So normal absorption of oxygen across the respiratory membrane at rest is about 250 mils of oxygen per minute. A normal alveolar ventilation is about 4 or 5 liters per minute, and you'll notice that the partial pressure of oxygen in the alveoli is about 104 millimeters of mercury. So this is the norm. So what would happen if I increase alveolar ventilation? So in other words, I'm bringing in more fresh air per minute, but I will not be changing the absorption of oxygen. So you just follow the red line. So it says if I increase ventilation, the partial pressure of oxygen in the alveoli will go up to a limit. There's only so much we can get. So ventilation, or ventilation rate, will affect the partial pressure of oxygen in the alveoli. If you increase ventilation, the levels of oxygen go up. You're bringing in more air. If you decrease ventilation, the levels of oxygen in the alveoli will decrease. So think about why the oxygen will decrease if you decrease ventilation. Why is it dropping? Because think about what's happening in the alveoli. You're still absorbing oxygen across the respiratory membrane. If you're not bringing in new air, the levels of oxygen are going to drop. Now, what about if we drop down to this blue line? So if we had kept ventilation the same, but I affected the absorption of oxygen across the respiratory membrane. So in this case, I've decreased the level of oxygen, or sorry, not decreased. I've increased the absorption rate of oxygen across the respiratory membrane, so say exercise. So during exercise, I may get to a liter of oxygen being absorbed across the respiratory membrane per minute. If I did not change ventilation, what would happen to the partial pressure of oxygen in the alveoli? Look, it's dropped significantly because you're moving that oxygen across the respiratory membrane fairly quickly, but you're not bringing in any new oxygen. So the partial pressure of oxygen would decrease. But I'm going to tell you, in real life, this does not happen. In real life, yes, you're going to increase this absorption rate of oxygen during exercise, but simultaneously, you will increase ventilation to match that. So what will happen is you will increase your ventilation to the point where you're back at 104 millimeters of mercury, because that does happen. We have very strong mechanisms, control mechanisms in place that the levels of oxygen in that alveoli should not change that dramatically. So we do try to keep it at 104 millimeters of mercury. But it's still important for me that you understand the effects of changes in ventilation and changes in absorption on the levels of oxygen in the alveoli, because later we're going to be looking at maybe problems with gas exchange, problems with ventilation. How would it affect the levels of these gases in the alveoli? So you should know what's the effects of ventilation alone on the partial pressure of oxygen and the effects of the rate of absorption of oxygen on the levels of oxygen in the alveoli. Now, what about carbon dioxide? Well, carbon dioxide will be affected by ventilation because you need to exhale that waste product out of your lungs. But in this case, also, it's going to be affected by the rate of excretion. So oxygen is absorbed, carbon dioxide is excreted. It's going to go from the blood out into the alveoli, and then you're going to exhale it out. So it's going to be influenced by the rate of excretion of CO2. So let's look at the graph here. So in the red represents the normal, what the normal effects of changes in ventilation on the CO2 levels in the alveoli, and this represents normal excretion of CO2. So this would be at rest. About 200 mils of CO2 is excreted at rest per minute at the respiratory membrane. So let's look at what's going to happen. So the normal alveolar ventilation, I said, is about 4 or 5 liters per minute. At this normal excretion of 200 mils of CO2 per minute, the partial pressure of carbon dioxide is about 40 millimeters of mercury. So what would happen to the partial pressure of CO2 in the alveoli if I increase ventilation? So I'm blowing more CO2 off. So you'll notice if you follow this down, partial pressure of CO2 will decrease because you're exhaling it out. If I decrease ventilation, CO2 levels will continue to climb because you still got exchange across the respiratory membrane. CO2 is going from the blood into the alveoli, but you're not exhaling it out, so the partial pressure of that CO2 will increase. in the alveoli. Well, what about the effects of changes in excretion? So during exercise, if I increase the excretion rate of CO2 to say 800 mils of CO2 per minute, what would be the effects of that on the partial pressure of CO2 in the alveoli? Well, what if I do not change ventilation? So if I don't change ventilation, but I increase the excretion rate, my partial pressure of CO2 is going to be way high. But we said, and normally we always try to match ventilation with changes in gas exchange. So what's going to happen in real life when your excretion rate of CO2 goes up? You will increase ventilation to the point where that CO2 in the alveoli is still going to be 40 millimeters of mercury. But again, it's just I had said for oxygen, I still want you to remember what would be the effects of changes in ventilation on the levels of these gases if I did not change the rate of exchange of these gases at the respiratory membrane. And also, if I did not change ventilation, but I changed the rate of gas exchange, what would happen to the partial pressure of these gases? We know in real life, we will always try to keep the levels of those gases pretty much constant. 104 millimeters of mercury for oxygen and 40 millimeters of mercury for CO2. So let's kind of like review it again. If the more rapid oxygen is absorbed across the respiratory membrane, the lower the concentration of oxygen in the alveoli. Okay, so we'll just look at this picture again. So the more rapid oxygen is absorbed, it's the blue line, the lower the partial pressure of oxygen in the alveoli. The more rapid new oxygen is breathed into the alveoli from the atmosphere, the higher the concentration of oxygen in the alveoli. Now, if you look at CO2, the alveolar partial pressure of CO2 increases in direct proportion to the rate in which CO2 is excreted. So if I keep ventilation the same and I increase excretion, it's going to increase. The partial pressure of CO2 in the alveoli will decrease inversely to alveolar ventilation. So if I increase ventilation, it will decrease. If I decrease ventilation, it will increase. So both gases are determined by rates of either absorption and excretion and the rate of ventilation. So when you look at the partial pressures of the gases in alveolar air, look, the levels of oxygen have changed, CO2 has changed, water vapor, it's pretty much completely saturated, so that's not going to change. But you'll notice oxygen and CO2 has changed. Oxygen is now 104 millimeters of mercury. CO2 is now 40 millimeters of mercury. And again, if it's circled in orange, you need to know that number. So think about again, why are these numbers different? Because at the respiratory membrane, oxygen is being absorbed, so it's going to be less than humidified air. CO2 is higher because CO2 is being excreted. It's going from the blood into the alveoli. That's why they're different. Now, what about exhaled air or expired air? When you exhale air, you're going to be mixing inspired air with the air that was in your lungs, that functional residual capacity. So you're going to be mixing new air with air that was involved in gas exchange. And so what's going to happen is you're going to have part new air, part old air. So the partial pressures of oxygen and CO2 are somewhere in between alveolar air and humidified air, because that certain amount of air that is in your tracheobronchial tree did not participate in gas exchange. The ones right down by the alveoli did. And so when I exhale my air, it's going to be a mixture of those two gases. So you'll notice you still have a pretty good amount of oxygen in exhaled air. So if you were trapped in a closed box, you would be able to survive for a certain amount of time because you still have oxygen. What's going to kill you generally is the buildup of CO2. That's generally what's going to kill you. So I'm not going to tell you, let's try to figure out how long you can last in a box, because we have to figure out the size of the box, how quick you're breathing, all that, but just pretty much know that you still got a good amount of oxygen in that air that you're exhaling. Now I've kept talking about gas exchange, and now I want to really look at where gas exchange takes place in the structure of the respiratory membrane. Now the respiratory membrane is composed of 6 layers, and even though it's 6 layers, it's pretty thin. The respiratory membrane is only about 0.2 to 0.6 micrometers in thickness. So think about why you would want such a thin respiratory membrane. You want very quick and rapid gas exchange. That's why we try to keep it as thin as possible. So let's look at the 6 layers, because you need to be aware of the 6 layers, and you must know if I ask you for oxygen, give me the order in which oxygen moves across the respiratory membrane. Which layer does it go through first? And then that second layer, the third, the fourth, the fifth, the sixth. But also if I asked you for CO2, which layer of the respiratory membrane does it go through? And then which is the last it goes through. So let's look at the 6 layers. So we'll kind of go 1 through 6 as in talking about oxygen. So inside the alveoli here is our oxygen. Oxygen first must diffuse through a layer of fluid and surfactant. And so that's going to be an important thing. Next topic we're going to talk about is how much of a gas can be dissolved in a fluid. Because in lining your alveoli, you do have a little bit of water mixed with surfactant. So it has to go through that first layer. The second layer it goes through, it must go through the epithelium of the alveoli. What type of epithelium line the alveoli? You should have learned it in cells and tissues. Is it simple columnar, simple cuboidal, or simple squamous? I hope you would be able to tell me which one it is. So it is simple squamous epithelium. You want it nice and flat. Third layer has got to go through the basement membrane of the epithelium. Okay? So first we're looking at the cellular structure of the alveoli it has to go through. Then next it has to go through some interstitial space. And in reality the interstitial space should be more of a potential space because these guys should be right next to each other. But there is a small amount of space it must go through. And then it's got to go through the cellular structure of the capillary. So you have to have the basement membrane of the capillary. Then you see in the blue, we have the endothelium of the capillary, which is just what we call the simple squamous epithelium that lines blood vessels, but it is the endothelium. And then we're done. That is the respiratory membrane. In reality, oxygen keeps going, but that's just the respiratory membrane. It's going to be dissolved in the fluid, in the plasma, and some of it then will be carried on hemoglobin in the red blood cell. But the 6 layers of the respiratory membrane is what you see here. CO2 will go in just the opposite direction. So CO2 will first go through the capillary endothelium and then the other direction. So it's got to get through 6 layers of the respiratory membrane. So you'll notice I had mentioned before that at some point in time, when you've got diffusion of these gases, they've got to go through fluids. So what determines the amount of a gas that dissolves in a fluid? So first thing I want to talk about is something called Henry's Law. Henry's Law tells us the relationship between the concentration of a gas in solution is directly related to the partial pressure of the gas, and we're talking the partial pressure of gas in the air or in the gaseous state, and also directly related to the solubility of the gas. So you'll see the equation down here. So the more soluble the gas, the more will be dissolved in solution. The greater the partial pressure of gas here, the more I'll be able to get into solution. And that's kind of a pretty important concept to think about. So if I have the same partial pressure for two gases, say CO2 and oxygen, which of the two gases will I be able to get more into solution? Well, I'm going to tell you right now that carbon dioxide is about 20 times more soluble than oxygen. So you have in your notes somewhere, it gives you what we call a solubility coefficient. You don't have to memorize those numbers. But if you sit there and you looked at them, you could pretty much realize and do a little bit of math that carbon dioxide is about 20 times more soluble. That's the number I want you to remember. So if I start off with the same partial pressure of those two gases, I'm going to get a lot more carbon dioxide dissolved in solution than I would with oxygen. Could I apply that to real life? Oh yeah. What do you think about when they make carbonated sodas? What do they use for carbonation? They don't use oxygen. They use CO2. Because CO2 is much more soluble than oxygen. Now, how did they carbonate that soda? Well, they know the principles of Henry's Law. Someone went to school. They took some chemistry classes. They bottle these under high pressure. So they have high pressure of CO2 in the gaseous state. They can force a lot of CO2 in that solution. Now, what do you think happens when you pop open that cap or that lid of your soda bottle? Well, the gas is going to go from the aqueous solution out to the gaseous state, because gases always want to go from its high concentration to low. So if you have a higher concentration of gases in aqueous solution than you do in the gaseous state, they will move out this way. If you have a higher concentration of gas in the gaseous state, it will go into solution. So think about what happens at the respiratory membrane. You got high concentration of oxygen in the alveoli, less in the blood, so oxygen goes into the blood. CO2, you got more CO2 in the blood than you do the alveoli, so CO2 will go from the aqueous state, across the respiratory membrane, and eventually out into the alveoli. So you see here again, so oxygen is going to go alveoli across the respiratory membrane. CO2 is going to go in the opposite direction. Now, other things that determine the diffusion of gas through fluids, and this is actually things that are going to influence the rate of diffusion of gas through fluids. I have to introduce you to another equation or law called Ficks Law. So you're going to notice with the respiratory system, you're having to know a lot of different laws. Today we've already done Dalton's Law, Henry's Law. Now we got to do Ficks Law. And yes, you're going to have to remember these for your exam. Okay? So Ficks Law shows us a relationship between various factors and the rate of diffusion of gas through fluids. I might as well mention now, even though the slide's coming up, is the biggest thing that determines the rate of diffusion of gases is it's through the fluid layers that you have when we talk about movement of gases across the respiratory membrane, then eventually into the blood or out of the blood in the other direction. It's not generally a problem with going through the tissues, because gases are freely dissolvable in lipids, and when you talk about membranes, it has no problem getting through membranes. So the biggest problem usually comes through its diffusion through fluids. So I have an equation. Don't think of it as math. Think again as a concept. It's going to show you a relationship for various factors, and the big D refers to diffusion rate. So what factors will influence the rate of diffusion of a particular gas? Well, one thing I do want to to emphasize here, I've circled it in orange. The S is the solubility of the gas in fluid. The MW is the molecular weight of the gas. And you'll see in the equations the square root of the molecular weight of the gas. I'm combining these together and kind of separating it out because that's going to be a constant for a particular gas. So this here is referred to as, say, a diffusion coefficient. It tells us you can have an idea about how quickly a particular gas will diffuse through fluids. And I have given you some numbers. You don't have to memorize these numbers, but you'll notice, look at carbon dioxide compared to oxygen. It has 20 times the diffusion rate as oxygen because it's pretty much 20 times more soluble. That's where a lot of it came into place. It's much more soluble in fluids than oxygen. So no matter, this is going to be a constant. If we're talking about oxygen or CO2 or nitrogen, if you have a particular gas, what other things can determine the rate of diffusion of that gas through fluids? So let's look at these other factors. The big A is cross-sectional area. So cross-sectional area we can think about when we refer to as the cross-sectional area of the respiratory membrane. Do we have a very large cross-sectional area or a fairly low? In reality, we have a very large cross-sectional area for gas exchange because our surface area of the membrane is about 70 square meters. It's humongous, okay? So, but according to this equation, if you increase the total cross-sectional area, the diffusion rate goes up. So it's pretty good that we have a very large cross-sectional area. If you decrease it, you will decrease the diffusion rate. So there's a direct relationship between cross-sectional area and diffusion rate. The other thing that has a direct relationship is the pressure gradient, the delta P. So delta P, or the pressure gradient, definitely has an influence on the rate of diffusion. The greater the pressure gradient, the greater the diffusion rate. The lower the pressure gradient, the lower the diffusion rate. The little d, now the little d is distance, and that's on the denominator of this equation. So there's going to be an indirect relationship between distance and the rate of diffusion. So according to this equation, if you increase the distance for that particular gas to diffuse, you will decrease diffusion rate. If you decrease the distance, you will increase the diffusion rate. So there's an indirect relationship here. So what type of things could we give you examples that would influence diffusion rate of either oxygen or CO2 that we can apply these to real life? So let's give you some real life things. I already went over that. So first thing is think about thickness of the membrane. Which of those factors in that equation would be influenced by the thickness of the membrane? That would be the little d, the distance. The thicker that respiratory membrane, the slower the diffusion rate. So what type of things can cause the thickness of the membrane to increase? If you've got edema, a buildup of fluid in the interstitial space, say if you have pulmonary edema, that can lower diffusion rate of the gases. And we had talked about that when we talked about the heart defects or the valvular defects. That definitely can have a huge role in diffusion rate of the gases. If you've got fibrosis, fibrotic changes in the lungs, some scar tissue, that could also decrease diffusion rate. Normally, that respiratory membrane is very thin, so it's pretty quick. Now, what about surface area of the membrane? According to that equation, it has a direct relationship. And I had said our surface area for gas exchange is fairly large. But any pulmonary disorder that decreases the functional surface area will decrease the rate of gas exchange, because some pulmonary disorders may destroy alveoli. So technically, your surface area will be influenced. It's going to be decreased. If you've got any kind of collapse of the alveoli, that would be could be destroying alveoli. That would slow down gas exchange. If you remove a portion of the lung, that would decrease gas exchange. The diffusion coefficient of the gas, now that's constant for a particular gas, so you can only use that if you want to compare oxygen, say, versus CO2. So CO2 diffuses at a quicker rate than oxygen. Now the other thing is the pressure difference between the two sides of the membrane. So the pressure gradient that you have. So if I, say, go to a higher altitude, the partial pressure of oxygen is going to be very much diminished in the atmospheric air. Partial pressure of oxygen in the alveoli is going to be much less than what you'd normally see. So that would decrease the pressure difference, which would affect gas exchange. That's why a lot of people cheat when they go up to, say, Mount Everest and they take canisters of oxygen with them because they can't handle it, and so they decide to use sneak in some oxygen so they can get some more oxygen into their lungs. If you hypoventilate, that also would decrease the pressure difference. So that's something that could influence the rate of gas exchange. Now, other concept that I want to discuss is the diffusing capacity for the respiratory membrane. I'm going to tell you, diffusing capacity is really good. And we're going to talk about it for oxygen and CO2. So we're talking about how much oxygen or CO2 can move across the membrane per minute for every millimeter of mercury pressure difference. So if we talk about diffusing capacity for oxygen, at rest, this is a number to put in the back of your head. At rest, about 21 mils of oxygen will move across that respiratory membrane per minute for every millimeter of mercury pressure difference. So I want to show you this little picture. Here's my little alveoli. This represents a pulmonary capillary. The partial pressure of oxygen coming into the lungs from your systemic circulation is only about 40 millimeters of mercury. We just used it in the tissue, so it's not going to be real high. It's about 40. So it comes in here, you have an initial gradient that's about 64 millimeters of mercury. So you're going to have pretty quick gas exchange, a very large gradient. So pretty quick gas exchange. By the time that blood leaves and goes past the alveoli, it will be fully equilibrated with what you have there in the alveoli. It will be 104 millimeters of mercury. So that will be the level of oxygen you'll have in the blood as it leaves the pulmonary circulation. Well, Guyton says, and I don't know how they figured it out, they said the average pressure difference is about 11 millimeters of mercury. I know the initial one's 64. At the end it's 0. I have no idea how they get 11, but they said the average pressure difference is 11 millimeters of mercury in the alveoli. So if you know the diffusing capacity, which is 21, it says I can get 21 mils of oxygen per minute across that respiratory membrane for every 1 millimeter of mercury pressure difference. I've got 11. So you multiply these two together, you get 231 mils of oxygen that move across the respiratory membrane per minute. That's very close to a number I told you to put in the back of your mind because I was going to mention it later. If you remember when we were looking at what could affect the levels of oxygen in the alveoli, we had said it could be changes in ventilation or changes in the rate of absorption. And I said the normal absorption rate for oxygen was about 250 mils per minute. That 231 is very close to that 250. So a lot of textbooks use that 250 mils per minute. So that's pretty close. That's kind of where they got the numbers. They knew the diffusing capacity for oxygen. Well, what do you think happens during exercise? What do you think may happen for the diffusing capacity for oxygen when you exercise? what do you want to happen? When you exercise, you need more oxygen. I hope I can get more oxygen to move across the respiratory membrane per minute. So what's going to happen is it can go up about 3 times the resting rate, especially for the young males can go up to about maybe 65 mils per minute per millimeter of mercury. So in exercise, the diffusing capacity for oxygen increases. A number of factors will play a role in it. You increase blood flow during exercise. You have better perfusion. Well, that's the same thing. You increase blood flow. You have better ventilation during exercise. So dormant capillaries are opened up. Total cross-sectional area, surface area improves. And so your diffusing capacity for oxygen across the respiratory membrane increases. What about if I asked you, do you think the respiratory membrane is efficient, fairly efficient? I would say, you'd probably say, well, yeah. Well, we've been designed to have a very efficient respiratory membrane. So let's look at this graph. This is telling you how much time blood has hung out in the alveolar capillaries and the partial pressure of oxygen that's measured in that blood compared to the alveoli. So if I have a heart rate of about 80 beats per minute, the blood will hang out in the alveolar capillaries only about 0.75 seconds. Well, that blood only hanging out there for 0.75 seconds will be fully equilibrated with the alveolar air, which is about 104 millimeters of mercury. That's pretty good for spending that little bit amount of time. It gets that oxygen because that gas exchange is fairly quick, fairly efficient. Well, it's even really efficient during exercise. If you're down to spending only 0.25 seconds in the lungs, that's maybe, if I did the math, maybe about 240 beats per minute. That's a pretty fast heart rate. You're still going to fully equilibrate the oxygen in that blood with alveolar air. That's good. You'll notice, though, we've put some examples where maybe you've got some issues. If you've got abnormal, if you've got some sort of lung disorder, problems with gas exchange, you may, if it's maybe slightly normal, under resting conditions, you may be able to get to 104 millimeters of mercury in that blood. But if you exercise, probably not so. If it's gross, you've got some gross problem, you will never be able to fully equilibrate the oxygen. So you've got some serious lung disorder. But normally, physiologically, our lungs are fairly efficient. We can fully equilibrate that blood in the lungs and even when extremes of exercise. So that's pretty good. Well, what about the diffusing capacity for CO2? Now, the diffusing capacity for CO2, they've never been able to measure. And the reason why it's never been measured, it's so fast. CO2, remember, is 20 times more soluble than oxygen. It's so quick they've never been able to measure it. But they've measured it for oxygen and other gases, and so they know a relationship between the diffusion coefficient and diffusing capacities, so they know that CO2 has got to be 20 times that of oxygen. So it's going to be 20 times whatever you got for oxygen. So oxygen was, what, 21? So it's going to be over 400 mils per minute per millimeter of mercury. So they've never been able to measure it, but we can guesstimate it because we should be about 20 times that of oxygen. But so how efficient is the respiratory membrane for the removal of CO2? We're going to see some little difference here. So normal conditions here. Got a heart rate of 80 beats per minute. You're spending about 0.75 seconds in the capillary. We're down to that 40 millimeters of mercury that we should have by the time we leave the lungs. In exercise, about 240 beats per minute. You're not quite there. The question is, if the diffusing capacity for CO2 is so much greater than oxygen, then why we're not at your goal of 40 millimeters of mercury when you spend, much less time in the capillaries? Well, it's going to come down to how carbon dioxide is transported. CO2, and we're going to be talking about that next lecture. The pressure gradient is much less in the lungs for CO2 than you have for oxygen. It's only 5 millimeters of mercury. Okay? Oxygen is over 60 millimeters of mercury. So there's a big difference in the pressure gradients, but also CO2 is transported differently than oxygen. The transport mechanism a little bit slower because it uses an additional transport mechanism from oxygen. And you probably maybe talked about a little bit in biochemistry when you talked about bicarbonate. So we're going to be talking about that next lecture. Now the very last topic, I love how this is screwed up, is the ventilation-perfusion ratio. So I want to talk about what this is and why we talk about it. It's a very quantitative concept. It was developed to help us understand gas exchange, especially when there's an imbalance between ventilation and blood flow. So this is the ventilation, the Q is the blood flow. So it's a concept designed to show us a relationship between what would happen if I affected ventilation or affected blood flow on the levels of gases that we get. So the ventilation-perfusion ratio this is the ideal ventilation-perfusion ratio. It should be 0.8. It's a unitless number because it's just a ratio. So how do they get it? Ideal alveolar ventilation is 4 liters per minute. Total blood flow, Q, is your cardiac output. That's 5 liters per minute. So 4 divided by 5 is 0.8. That is an ideal ventilation-perfusion ratio. Big thing I want you to always remember is we always want to match our ventilation with the blood flow. If I'm bothering to bring in air into my lungs, I want to be able to have the gases exchange and be transferred from point A to point B. I want to match the blood flow in my ventilation. I do not want to waste any ventilation, and I also don't want to waste my blood flow going to an alveoli that perhaps is not getting well ventilated. So you always want to maintain this optimum ventilation-perfusion ratio. All right, so here, I want you to look at this picture. Start here in the middle, because this is kind of can be very, very confusing. And my predecessor used to always call the ventilation-perfusion ratio the ventilation confusion ratio because it can be confusing. So we're going to try to take it a little bit slow. So in the middle, this is normal. This is the partial pressure of oxygen in the alveoli. This is the partial pressure of CO2 in the alveoli. Now I don't have the units here. You know I'm big on units, but I just didn't have room for it. So these are all millimeters of mercury. Here's the normal ventilation-perfusion ratio. So I want to look at different scenarios. Now again, before we look at the different scenarios, 2 factors that can determine the partial pressures of the 2 gases in the alveoli will be changes in ventilation and the rate of transfer across the membrane, something that we talked about the earlier part of the lecture. So, first scenario, we're going to look at the extremes. So first scenario, let's do way here to the left. The first scenario, I have cut off my ventilation. I have plugged this up. I don't have new air coming in. So my numerator will be 0. So 0 over 5 liters per minute will be 0. So my ventilation-perfusion ratio in this scenario is 0. Well, you'll notice that the partial pressure of the gases in the alveoli, these are the same numbers for the partial pressures of the gases that you would see in the blood that was coming up here from the systemic circulation. Because what's going to happen is we're going to get fully equilibrated here. This is going to equilibrate with what you have in the blood. The partial pressure of oxygen in that venous blood is 40 millimeters of mercury. And I'm talking venous blood as coming from the systemic circulation. I know it's the pulmonary arterial blood. The partial pressure of CO2 is 45 millimeters of mercury. So just compare it to the ideal. The partial pressure of oxygen is much lower. CO2 is higher. Close your eyes. Think about it. Why is the partial pressure of oxygen less than the ideal? Because you're not bringing in new oxygen. The oxygen was still moving across the blood going this way. You have no new air coming in, so the partial pressure of oxygen is going to be less. CO2 will be greater because carbon dioxide is going to be coming from the blood into the alveoli, and it's not being exhaled out. So it's sitting there. So partial pressure of CO2 will be greater than you see under the ideal ventilation-perfusion ratios. So what if you have somewhere in between, which in reality is what we're going to get? Anything that influences ventilation, if it decreases alveolar ventilation, you will have ventilation-perfusion ratios of less than 0.8. And your partial pressure of oxygen will be less than the 104 millimeters of mercury, and the carbon dioxide levels will be greater than the 40 millimeters of mercury. Because we had mentioned earlier in the lecture that if you impair ventilation, that definitely affects both oxygen and CO2. So without proper ventilation, you cannot bring in the oxygen, and you can't get rid of the CO2. Now, what will happen though in real life, if the partial pressure of oxygen gets less than 70 millimeters of mercury, you will shunt the blood away from that poorly ventilated alveoli. So we have what we call a physiological shunt. So we do not want to waste that blood flow. So we will constrict the vessels that are serving the alveoli so we don't have this going on. If this happened and I didn't shunt that blood, the levels of CO2 in your blood are going to go up and the oxygen levels will be less. So if it gets too low, we will constrict blood vessels serving those poorly ventilated alveoli. If you look at the other extreme, ventilation, fine, but we've cut off blood flow. So on the denominator, the Q, it's 0. If you put 0 on a denominator, you're going to get infinity. So here, our ventilation-perfusion ratio is infinity. So what we have here, if you look at the partial pressures of the gases in the alveoli, the partial pressure of oxygen in the alveoli is what you would get in humidified air. Now this one we have 0, but it should be 0.3 millimeters of mercury. The partial pressure of CO2 in humidified air is 0.3 millimeters of mercury. So what you'll have is, if you have absolutely no blood flow, you've got the air coming in, the humidified air, but you don't have gas exchange. So that's why you get the partial pressures of the gases that you would have normally seen in humidified air. So anytime you have problems with blood flow, you'll notice that the partial pressure of oxygen will be higher than normal in the alveoli. The partial pressure of CO2 will be less in the alveoli than normal, because again, you're not getting the exchange across the membrane. So if we have conditions where don't completely block blood flow but somehow reduce blood flow, you will always have what we call increasing ventilation-perfusion ratios. It'll be greater than 0.8. The partial pressure of oxygen will be higher than the 104 millimeters of mercury, and the partial pressure of CO2 will be less than that 40 millimeters of mercury. So ventilation-perfusion ratios, we do, believe it or not, under normal conditions, have areas in our lungs that don't have this ideal ventilation-perfusion ratio. We have differences in a normal upright lung. So I want to show you this picture to kind of show you why we have differences in a normal upright lung in regards to ventilation perfusion ratios. You have, because of the effects of gravity, we have differences in the pleural pressures as we go from the apex to the base of the lungs. And if you kind of zoom in and look at the lung tissue, because of the differences here, this is just someone just exhaled. You'll notice that we have what does the game say? The alveoli are more inflated up here at the apex than down here at the base. And it's because, not just because of this, the pleural pressures, is the transpulmonary pressure is greater up here. But what's so significant here, it actually makes that part of the lungs less compliant. You're already kind of stretched that to its limit. You're not going to be able to get as much new air in up here than you would here. So we do have differences in ventilation in a normal upright lung, but the thing that's going to cause the huge disparities in, I don't want to say huge, but the differences in the ventilation perfusion ratio is going to come from the differences in blood flow. So there is differences in blood pressure in a normal upright person. Blood pressure is always greatest down here than up here. And you have much better blood flow at the base of the lung, way much better blood flow at the base of the lung than you have up near the apex. So because of the differences in blood flow, yes, slight differences in ventilation, you have differences in the ratio in a normal upright lung. So if you look at this picture, this would be the base of the lungs, this is the apex of the lungs. If you notice down at the base of the lungs, if you follow this down right here, the ventilation perfusion ratio is less than the ideal. It's got a low ventilation perfusion ratio. At the higher part, or the apex of the lungs, the ventilation perfusion ratios are high. So there's differences in ventilation perfusion ratios from the apex to the base of the lung. So let's see how that comes out, or how that influences the levels of oxygen and CO2 in those areas of the lungs. So let's look down at the base of the lungs. That has lower ventilation perfusion ratios. Well, if you go back to that earlier picture and we're looking at how ventilation perfusion ratios affect the partial pressure of the gases, you're going to see the same thing they're about to see now. At the low ventilation perfusion ratios, CO2 levels are higher than normal, oxygen levels are lower than normal. At the apex of the lungs, where they have high ventilation perfusion ratios, the partial pressure of oxygen is higher than normal, and the CO2 is lower than normal. So there's differences in a normal upright lung. Here's where we would have the normal, the ideal. This does not really play a significant role when we talk about the partial pressures of oxygen, CO2 in your blood, because all these different bloods are going to mix together by the time you leave the lungs, and you're going to be at that normal, everything will average out, and you'll get the partial pressures of oxygen and CO2 that you'd see under ideal conditions. Now, what I do want to mention, maybe I can bring in maybe some microbiology. If you notice up here, up at the apex of the lungs, the partial pressure of oxygen is much higher. So there's certain bugs or certain infections that you'll see more up in the upper part of the lungs because of the high levels of oxygen. And maybe you might be able to apply it to certain things that don't like oxygen. You're not going to see them up here affecting the upper part of the lungs. They may be more at the lower part of the lungs. So you have much higher oxygen up here, and certain things that love oxygen are going to want to hang out up here, the upper part of the lungs. Now, what about conditions? Or what about exercise? I'm going to give you during exercise. Now during exercise, what's going to happen is you're going to have changes in blood flow. You're going to have much improved blood flow through all parts of the lungs. You're going to have improved ventilation during exercise. And what will happen is everything's going to become more ideal. That's what we want. You're going to be able to get more oxygen, get rid of more CO2 during exercise, which is what you'd want. Well, what about pathologic conditions, which may influence blood flow or influence ventilation? Now, I have to go back, see if I can find it, to this picture here, where if you have this scenario over here where you have problems with blood flow, they usually refer it to as physiological dead space, because this is what we call wasted ventilation. You normally have what we call anatomic dead space, where you have air, but you don't have gas exchange because you're not down at the alveoli. So remember in the tracheobronchial tree, wherever there isn't alveoli, there are not going to be any blood vessels there for you to have gas exchange. So you do have dead space, and this is kind of dead space not because it's anatomic, because we do have alveoli, but because of the lack of blood flow, it is dead space, but they don't call it anatomic dead space anymore. They're going to refer to it as physiological dead space. Okay? So here, this definitely can happen with a number of different lung disorders where you get damage to the blood vessels that are serving the alveoli, but it also can get some of the alveoli that will collapse, and so you will not have gas exchange, such as emphysema. Now you can have conditions where you do just maybe I swallow something and it gets down into one of my bronchi or bronchioles, and you can have problems with ventilation, and you'd have a condition we'd see over here. But so you can have conditions, pulmonary disorders that affect both of them though. So both things can be affected under certain abnormal conditions.